Jai Hind to all. Today I am going to talk on the topic steady state error. So what is a steady state error? The deviation of actual output from the reference input during the steady state can be defined as the steady state error. So we can define, and it can be represented by this. ESS is equals to, steady state error is basically represented by ESS, which is equals to limit t tends to infinity ET if we talk about the time domain, and for the frequency domain it is limit s tends to 0 s into ES. So steady state error will be defined as the deviation of output of the control system from desired response during the steady state, known as the steady state error. As steady state error is the index of accuracy of any control system. So the error should be, steady state error should be as minimum as possible, right? This is the block diagram that I have taken to derive the expression for the steady state error. This is the closed loop control system with unity feedback, and it is having a negative actually feedback. So as we know, the transfer function of this particular system will be Cs upon Rs, and it is coming out to be Gs upon 1 plus Gs. Okay, and you can see here the difference of output and input is the error signal. So from this diagram we can write that Cs will be equal to Es into Gs, okay, and this is Cs, okay, and we can also write that Es will be equal to Rs minus Cs. So we can write Es is equals to Rs minus Cs. So let's put the value of Es from this equation number 1 into equation number 2, right? So that means let's put the value of Cs from equation 2. We will get Es is equals to Rs minus Es into Gs. So from here we'll take common Es. So it will be, Es into 1 plus Gs is equals to Rs. And so from here I can write Es upon Rs will be equal to, Es upon Rs will be equal to 1 upon 1 plus Gs, right? And from here we can write Es will be equal to Rs into 1 upon 1 plus Gs. So steady state error will be, let me complete it in the next expression, so from here, let me do here, Es will be equal to Rs upon 1 plus Gs, okay, and steady state error will be defined as limit s tends to 0 s into Es. So we can define steady state error limit s tends to 0 s into Rs upon 1 plus Gs. Okay, so steady state error will be Es is equals to limit s tends to 0 s into Rs upon 1 plus Gs from here, since this is the formula for the steady state error. Okay, so since the steady state error is comes during the steady state, so the coefficient of steady state error also called as the static error coefficients, right? So this is the steady state error that I have calculated in previous slide. So let's calculate the static error coefficient. So these static error coefficients are actually the positional error coefficient, ramp error coefficient, and the acceleration error coefficient, right? And these are specified for a particular input. Positional error coefficient is specified, will be always be calculated positional error coefficient, also known as the Kp. Okay, it will always be calculated for that unit step function. Positional error coefficient is associated with, it is always associated with unit step function. Okay, similarly, displacement error coefficient, displacement and positional are one thing. Velocity error coefficient is always associated with velocity error coefficient. It is represented by Kv, and it is always associated with unit ramp function. And the third one is, this is the first, second, and the third one is, this is second, this is first, is acceleration error constant. Error constant or coefficient, and it is all represented by Ka, and it is always associated with unit parabolic function. So let's talk about all these error coefficients one by one. So let's take the positional error coefficient, that is Kp. Okay. So as we know that steady state error is ESS into is equals to limit S tends to 0 S into RS upon 1 plus GSS. So for positional error coefficient, as it is associated with the unit step function, right? Unit step function. So the value of RS will be equal to here 1 by S. So let's put this value in this equation. Let's say this is equation number 1. Okay. So put value of RS in equation 1. That is the equation for the standard equation for the steady state error. So ESS will be equal to limit S tends to 0, right, into S into RS will be 1 by S, okay, into 1 upon 1 plus GS. Okay, so this S gets cancelled out with each other, and we can write here ESS will be equal to 1 upon 1 plus limit S tends to 0 into GS. S tends to 0. So we can write this term as, this term can be written as ESS will be equal to 1 upon 1 plus Kp. Okay, where this Kp will be equal to limit S tends to 0 into GS, right? So the steady state error will be, for positional error coefficient, the steady state error will be 1 upon 1 plus Kp, where this Kp is a error constant, positional error constant, and its value is equal to limit S tends to 0 into GS. Now talking about the second one, that is velocity error coefficient. Okay, again for velocity error coefficient, which is represented by Kv, right, though it is associated with unit ramp function. So the value of RS here will be equal to 1 by S square, right? Now put this value of RS, put value of this RS in equation 1 again, in that equation, in the equation of steady state error. So it will be, ESS will be equal to limit S tends to 0, okay, S into, what is RS here? 1 by S square Okay, we can give here bracket here also. I can make bracket. Okay, into 1 upon 1 plus GS. Okay, 1 plus GS. Okay, so 1s gets cancelled out here, and we can write this ESS will be equal to 1 upon limit s tends to 0 into s plus limit s tends to 0 1 plus GS. So you can see here it becomes 0 and this term is left out because we don't know the exact value of GS. So we can write here ESS will be equal to 1 upon limit, 1 upon limit s tends to 0 s into GSS. And where also this can be written as ESS will be equal to 1 upon kV, where kV will be equal to 1 upon, where kV will be equal to limit s tends to 0 s into GS. So kV is the static error coefficient, that is velocity error coefficient, and for this velocity error coefficient, the steady state error will be 1 upon kV. Now talking about the acceleration error coefficient. This is represented by Ka. So for acceleration error coefficient, to find out the value of Ka, this acceleration error coefficient is associated with the unit parabolic function. So the value of input here, that is input here is a unit parabolic function. So the value of unit parabolic function is 1 by s cube. Now put this value of parabolic function in this equation number 1. Put value of Rs in equation 1. Okay, so we will get ESS is equals to limit s tends to 0 1 upon, this will be, so this will be s into 1 by s cube into 1 upon 1 plus GS. Okay, so here only one s gets cancelled out here. So we are left with s square, 1 by s square in the denominator. So we can write here ESS will be equal to 1 upon limit s tends to 0, and the term left here is s square plus limit s tends to 0, this is 1 plus GS. Okay, so this becomes 0 and this term is left out. So we can write ESS is equals to 1 upon limit s tends to 0, s square will get multiplied with here. Similarly here, this is kV is this, s square will also get multiplied here, na? Because s square here is common for 1 plus GSHS. We are left here with s square into 1 plus GSHS. This is not plus. Okay, I'm sorry. There is something. So no, this is wrong. So here this we are left with 1 upon limit s tends to 0, okay, and s square into 1 plus GS. Now right, okay. So this, when this get multiplied, so we are left with 1 into limit s tends to 0 into s square plus limit s tends to 0 into s square into GS. Now this will be okay. So this term will become 0 and this is left out. So we are left out with 1 upon 1 plus limit 1 upon limit s tends to 0 s square into gs. Okay, and we can write it as ESS is equals to 1 upon Ka, right, where this Ka is equals to limit s tends to 0 s square into gs, right. So for kV it is limit s tends to 0 s into gs, where ESS will be 1 upon kV. For acceleration error constant, a steady state error comes out to be 1 upon Ka, where Ka is equals to limit s tends to 0 s square into gs. So you can see this is the summary for the static error coefficient. When we have applied the unit step signal, so the steady state error will come out to be 1 upon 1 plus Kp, where Kp is an positional error constant whose value will be equal to limit s tends to 0 into gs. When we have taken the unit ramp signal, the steady state error comes out to be 1 by Kv, where Kv is equals to limit s tends to 0 into s into gs. And when we have taken the parabolic input signal, the steady state error comes out to be 1 by Ka, and the value of acceleration error constant will be equal to limit s tends to 0 into s square gs. Now next we will discuss about the type of the control system. Okay, so consider this unity feedback control system which is having open loop transfer function. The value is k into TAS plus 1 into TBS plus 1 up to TMS plus 1 upon s raised to the power n into T1s plus 1, T2s plus 1, TP till so on till TPS plus 1. So type of the system can be defined as the number of pure integrator in the forward path of a unity feedback system, right? That is the type from this function. Type of the system will be defined by this n, the value of n, right? If the value of n is 0, then the type of the system will be 0. If here s raised to the power 1, then the type of the system will be 1, and so on, right? So it basically involves the term s raised to the power n in the denominator, which is basically representing the pole of the multiplicity n at the origin, right? Pole at origin. So our system is called type 0, type 1 and type 2 up to so on if n is equals to 0, 1, 2 respectively, right? As the type increases, accuracy of the system will also improved, right? For the control system, right, we will here talk about the type 0 system, type 1 system and the type 2 system. So I'll discuss these three types of the control system one by one. Now coming for the type 0 system. Let us consider the transfer function, open loop transfer function of a closed loop system will be this gs is equals to k into 1 plus t z1 into s, 1 plus t z2 into s up to so on upon s squared. Oh, this must be s raised to the power 0. Okay, s raised to the power 0, 1 plus tp1s plus into 1 plus tp2s up to so on, right? So I will discuss the type 0 system for all the inputs, for the step input, for the unit parabolic input and for the unit velocity inputs, right? So when the input is a unit step input, right? For unit step input, what we will find? Kp, right? So value of Kp will be for unit step input, that is limit s tends to 0 into gs. We simply put the value of this gs in this equation. So it is coming out to be limit s tends to 0, okay, and this is k into 1 plus t z1 into s into 1 plus t z2 into s up to so on upon, this is s raised to the power 0 means nothing, that is 1, 1 into 1 plus TP1 into S, 1 plus TP2 into S, sorry, this is S, up to so on. So when we put this limit S raised to the S tends to 0 in these terms, this term will become 0, this will become 0, all these terms will become 0, and we will get the value K. Simply here Kp will be equal to K for this, right? And so the steady state error will become, what will be the steady state error? That is 1 upon 1 plus Kp. Okay. So we can simply put the value of Kp in this equation, that is 1 upon 1 plus K will be the steady state error for this system, for the type 0 system. Similarly, for type 0 system, let the input is kV. Let input is unit ramp input. Okay, unit ramp input. For unit ramp input, what will be the value of kV? That is limit S tends to 0, S into GS. Now we can again simply put the value of GS in this equation. So it is limit S tends to 0, right? For type 0 system, when we have taken the unit ramp system, I am calculating the value of kV and simply putting the value of GS, that is K into 1 plus TZ1 into S, 1 plus TZ2 into S up to so on, upon S raised to the power 0 means 1 into 1 plus TP1 into S, 1 plus TP2 into S up to so on, right? So when we will put the value of S tends to 0 in this equation, so this equation will become 0, the value will become 0. That means here kV is equals to 0, right? And correspondingly the value of steady state error for kV is 1 upon kV. So the steady state error will become infinite. Okay. So from here steady state error will become infinite. Similarly, we can find out the value of Ka for unit. Let input is unit parabolic system. Okay. Then the value of Ka will be limit S tend to 0 S square into GS. Okay. So when we put the value of GS again here, and because of this S square, we will put the value of S is equals to 0. So it come out to be 0. Ka will become 0 for this case when we put the value of GS because of this S square, right? So again, the steady state error for this case will become infinite. So for type 0 system, right, the steady state error for positional error coefficient will be 1 upon 1 plus K, right? And for unit ramp input, for velocity error constant will be infinite, and for acceleration error constant also it will become infinite. Okay. Now coming to the type 1 system. So the type 1 system, let us take the value of GS will be S raised to the power 1 here. Okay. So this is S raised to the power 1, that means there is one pole at origin and it will define the value, that is type 1. Okay. So the value of GS will be here K into 1 plus TZ1S, 1 plus TZ2S up to so on upon S raised to the power 1 into 1 plus TP1S, 1 plus TP2S up to so on. Now for again here for we'll calculate this for unit step input, right? We will again, that means Kp will be equal to here limit S tends to 0 into GS. And when we put the value of GS from the above equation in this equation, then it is K into 1 plus TZ1S, 1 plus TZ2S up to so on upon S into S raised to the power 1, that means S, 1 plus TP1S into 1 plus TP2S up to so on. So because of this value, all these terms will become 0, right? But k upon s1, because of this s, it will become infinite. Kp will become infinite, right? And correspondingly, steady state error will be 1 upon 1 plus infinite. That means 0 for this case. Now for type 1, we will calculate for unit ramp input. For unit ramp input, value of kv will be equal to limit s tends to 0 s into gs. Okay, so we will again put the value of gs in this equation. So while putting the value, kv will be equal to limit s tends to 0 s into the value of gs will be k into 1 plus t z1s 1 plus t z2s up to so on upon s raised to the power 1 plus t p1s 1 plus t p2s up to so on. So this s gets cancelled out with this term, and all these terms as well as associated with s will become 0, and we will get here the value of kp is equals to k. Correspondingly, the steady state error will be 1 upon kv, which is equals to 1 upon k for unit ramp input. And for unit parabolic input, we will find out the value of Ka, which is limit s tends to 0 s square into gs, right? So value of Ka, when we put the value of gs here, only one s from the numerator will get cancelled out from the denominator s. So the value of this will become 0, Ka, and correspondingly the steady state error will become infinite for this case. So now coming for the type 2 system. Type 2 system, this will be the value of gs, and when we calculate the value of kb for unit ramp input, that is limit s tends to 0 into gs, it is coming out to be limit s tends to 0 k into 1 plus tz1s into 1 plus tz2s up to so on upon s square into 1 plus t p1s 1 plus t p2s up to so on. So it will become, the value because of this s square will become infinite, and correspondingly something upon 0 is infinity. Steady state error is coming out to be 0, right? For similarly, we can calculate the value of velocity error constant for unit ramp input, that is the square s into gs. So when we put the value here, it is again coming out to be infinite. Let me find out the value, put the value here, 1 plus tz2 into s up to so on, and for this we have s square. So only one get cancel out, one s at the pole, right, get cancel out, so one is left. So again here we will get the value as infinite. Okay, so these terms will become again 0 because limit s tends to 0, and we have left with limit s tends to 0 k upon s. When we put the value limit of s here as 0, we will get the value of kv is equals to infinite, right? And correspondingly steady state error will become 1 upon kv, which again become 0. Okay, now we can calculate the value of Ka, acceleration error constant, which is limit s tends to 0 s square into gs. Now here it will get cancelled out, s square into k into 1 plus tz1s 1 plus tz2s up to so on upon s square into 1 plus tp1s 1 plus tp2s up to so on. So it becomes cancelled and all these terms will become 0. So what we will get? Ka is equals to k. Similarly, the steady state error now 1 upon Ka will become 1 upon k. Okay. So what we have concluded from all these, as the type of the system will increase, the steady state error will goes on decreasing for a particular input. You can see for type 0 system, we have steady state error that is 1 upon 1 plus Kp. And for type 0 system, 1 system, for step input only, steady state error will become 0. And again, for type 2 system, for step input, the steady state error will become 0. Right? And for ramp input, the steady state error for type 1 system, type 0 system is infinity. Then it reduces to 1 by kV for type 1 system and it further reduces to 0 for type 2 system. And in case of parabolic input, the error earlier for type 0 system is infinity. Again it is infinity and it reduces to the value of 1 by Ka for type 2 system. Okay. Similarly, these constant, you can see the value of this constant. Kp here is constant and it becomes infinity in type 1 system and it again remains infinity in type 2 system. Similarly, you can see the other values as well. So this is it for today's lecture. In next lecture, I will discuss about the, I will discuss some numericals based on these type of the system and the steady state error. Thank you.